In this lesson, we're going to continue our study of integrals of vector functions. In this problem, I've given you the acceleration vector of an object in motion, and I tell you the initial velocity and position, or the velocity and position at time 0, and I ask you to find the position vector of the object. So I want us to find the vector r of t that describes the position of the object at time t. So the first thing I remember is the relationship between position, velocity, and acceleration. So I know that velocity is the derivative of position and acceleration is the derivative of velocity. So again, velocity is the derivative of position and acceleration is the derivative of velocity, which is of course the second derivative of position. So here I have acceleration and I want to find position, which means instead of differentiating, I need to integrate. So the first thing I'm going to notice is that, okay, to find my velocity vector, I'm going to integrate my position vector, my acceleration vector. So this gives me integral of acceleration, so integral minus 1, 1, minus 2, and again, if you prefer the IJK notation, that's fine as well. So I need to integrate the acceleration vector to get velocity. So when I integrate, I'm going to get minus t, minus 2t, but remember when we do an indefinite integral, we pick up that constant vector that we saw in our definition. So we're going to get plus a c1, c2, c3. And again, that becomes because every time we do a definite integral, we get an arbitrary constant. So we get for our v of t, so we get our velocity vector, is minus t plus c1, t plus c2, and minus 2t plus c3. Now in this case, we know our initial velocity, so we know the velocity at time 0 was given to us to be the vector 1, 0, 3. So our velocity at time 0 was 1, 0, 3, and I can use that to solve for the c's. So if I actually take the expression that we found for v of t and plug in t equals 0, we get a c1 in the first component, a c2 in the second component, and a c3 in the third component, again when we plugged in t equals 0 in our expression for v of t. So now this tells me that c1 must be equal to 1, c2 is equal to 0, and c3 is equal to 3. So that tells us our velocity vector is v of t equals negative t plus 1, t, and minus 2t plus 3. So we now have our velocity vector that describes the velocity of our object at time t, but we wanted the position vector. So we need to integrate one more time. We remember velocity is the derivative of position, or position is the integral of velocity. So we're going to integrate one more time. So r of t is going to be the integral of our velocity vector. So we're going to integrate component-wise again. So when we integrate the minus t plus 1, we get negative a half t squared plus t, and then we know we're going to get that plus constant vector on the outside, so I'm just going to go ahead and put our constant in, and I'm going to put a d1 since we already used a c. When I integrate t, we're going to get a half t squared plus d2, and when we integrate minus 2t plus 3, we get negative t squared plus 3t, and I'll put a d3 here. Now again, we were told the initial position, r of 0, is equal to, so we were told our initial position was 2, 1, minus 4. So r of 0 is 2, 1, minus 4. And again now, to solve for the d's, let's take that position vector we were given and put in t is 0. So in the first component, we just get d1. In the second component, we just get d2. And in the third component, we just get d3. So this tells us that our d1 is equal to 2, our d2 is equal to 1, and our d3 is equal to minus 4. So we now know all of our arbitrary constants, so we get for our position vector, r of t is equal to negative a half t squared plus t plus 2, 1 half t squared plus 1, and negative t squared plus 3t minus 4. So we've now found the position vector that describes the motion of the position of the object at time t. Again, you can write this out in IJK notation if you prefer. So to summarize, the key steps to this problem were we started with our acceleration vector and we said, well, we know these important relationships between position, velocity, and acceleration. We knew that acceleration is the derivative of velocity, which means if we want velocity, we need to integrate acceleration. When we integrated acceleration, we got a vector consisting of arbitrary constants, which we got from our indefinite integral. We were able to use the given initial position to figure out what the values of each of those constants were. So we found C1, C2, C3. That gave us our velocity vector with no arbitrary constants. We then did the same procedure. We said, well, velocity is the derivative of position, so position is the integral of velocity, so we integrated our velocity vector. Again, we got arbitrary constants from the indefinite integral, used our initial position to find the values of those arbitrary constants, which in the end gave us our final position vector as a function, a vector function of time. Now you can check, so actually plug in, make sure that your acceleration vector is -1, 1, -2, your initial position and velocity. So you can check that this position vector actually satisfies the conditions given in the problem.